In this video, we're going to cover section 9.10 on synthesis strategies. And for the remainder of this course, we're going to be always ending each section with a discussion on synthesis, and specifically the synthetic utility that new reactions in that section provide for the synthesis of organic compounds. So in this chapter, this section, we looked at different ways in which we could react alkynes. And one of the reactions that we looked at in detail was hydrogenation reactions, or reducing alkynes. And we saw that there was various ways in which we could reduce an alkyne depending on what product we wanted to obtain. So if we want to form an alkane, we saw that we could use the same conditions that we saw for hydrogenation, catalytic hydrogenation of alkenes. And so if we use catalytic hydrogenation in the same way, we can form the alkane. Now what was new to this section is that we looked at two different ways in which we could go from the alkyne, but stop the reaction at the alkene. And there's two methods depending on the stereochemical outcome that we wished to obtain. So if we prefer to form a cis alkene, meaning syn addition to the alkyne to give us a cis alkene, we chose hydrogen in the presence of a less reactive or less efficient catalyst, a poison catalyst, that is Lindlar's catalyst. So that would obtain, or from that reaction, we would obtain a cis alkene. Now, if we wanted the trans alkene as our product, then we used the dissolving metal reduction, where we use sodium metal in liquid ammonia to obtain that trans alkene. And of course, if we wanted to further hydrogenate the alkene to the alkane, we could do so under catalytic conditions as we saw for this path. Now, how about the other way around? Are there methods in which we could take the alkene functional group and transform it to an alkyne? Well, we can do that, but we can't do it in a single step, and that's shown on the next slide. So you can see that one way in which we could produce, or a common way to produce an alkyne from an alkene, is to first halogenate the alkene with molecular bromine. And so under those conditions, you can see here we have molecular bromine, carbon tetrachloride is a solvent, sometimes shown in the text, sometimes not. And what we obtain from that would be the dibromo alkane. Now it's seemingly we are going in the wrong direction. We now have no pi bonds where we wanted to obtain 2 pi bonds in that of the alkyne. But don't fret, what we can do now is because we have the dihalogen alkane, we can undergo 2 successive E2 reactions to form our alkyne. So recall that one common way to prepare an alkyne is from a dihalo alkane. And so that's exactly what is shown here, is that the second step after forming the dibromo alkane, we use excess sodium amide to generate that alkyne. And then if necessary, if there is a terminal alkyne being formed, we would carry out a water quench to, in a sense, react with any additional amide present in solution and to protonate any terminal alkyne. And so you can see that we have either one-step reactions going in this direction or multiple step reactions that we can use to synthetically transform the alkyne to the alkene or the alkene back to the alkyne. Also in this section, we've learned an important reaction referred to as alkylation, which is a convenient way of increasing the size of a carbon skeleton via a carbon-carbon bond-forming reaction. And we're only going to look at a few carbon-carbon bond-forming reactions. And so these are synthetically useful when your target molecule has more carbon in it than your original starting materials. This is a typical way of carrying out synthesis. We start with feedstocks, small molecules, compounds containing few carbons, and we will successively increase the size of that carbon backbone using variety of carbon-carbon bond-forming reactions. Well, this is the first one that we'll look at, and an important one. And you can see that alkylation requires a terminal alkyne that we can deprotonate, generally in the presence of sodium amide, to generate the alkynide ion. And then we can add to it a primary alkyl halide or methyl halide to increase that carbon skeleton size. And so you can see in this example, starting with a 4-carbon unit of the alkynide ion and reacting with some generic alkyl halide that contains, in this case, 3 carbons. In effect, what we're doing is we're summing those 2 carbon parent chains to give us an overall system that contains 7 carbon atoms. And so alkylation becomes a really useful way for, again, increasing the size of your molecule towards your target. Now let's look at a synthetic route type question where we are given a starting material and asked to devise a synthetic route in order for us to transform into some target molecule. And in these questions, we won't be able to carry out the transformation in a single step, but will require a route that normally involves a few steps in order to prepare that target system. So the first thing I always recommend students look at is the size of the target molecule relative to the size of your starting material. Because if there is an increase in the carbon skeleton, that right away tells you that you must carry out a carbon-carbon bond forming reaction at some point during your synthetic route. So you can see in this example, we have a alkenyl substituent which is 2 carbons in length. But in our target molecule, we see that the size of that substituent has increased by 1 carbon. So we go from an ethenyl substituent to a 1-propenyl substituent. And so that tells us that we must carry out a carbon-carbon bond forming reaction at some point to increase the size of that carbon skeleton. So in this section, we've seen that we can use alkylation to carry out that type of process to increase the size of a carbon skeleton. Now, alkylation requires the formation of a alkynide ion and reaction of it with appropriately sized alkyl halide. So starting from an alkene, we're first going to have to transform that alkene to the alkyne so that we can generate that alkynide ion. Then we can increase the carbon skeleton size, and then from that larger alkynyl substituent, we can then reduce that in a controlled manner to give us this particular alkene. So let's put that into practice. Let's look at our synthetic route for this particular question. So in order to form that alkyne initially, we're going to need to brominate the alkene to the dihaloalkene. So we can use molecular chlorine or bromine, but generally bromine is used quite often in the text. Solvent, most likely carbon tet or some other chlorinated solvent. And the net result is we will form our dibromo alkynyl substituent or alkyl substituent. So in synthetic route type questions, it's not important for us to show the mechanistic details. That's left to those one-step syntheses, if you will. We look at those details for one step, but when we're doing synthesis, we don't show the mechanistic details. We just show the reagents that are used to transform from one species to another, and we only show the major product that's formed as a result of using those reagents. So now that we have formed our dibromo alkyl substituent, we can convert this to an alkyne if we use a strong base like sodium amide. So let's do that. So we can, in the first step, use excess sodium amide and liquid ammonia. And that will undergo 2 successive E2 reactions. And we use excess again to ensure that we push this reaction to completion. We're going to push it actually all the way to the alkanide ion. Now, we could quench with water, and that's typically what's done, so that we end up with our terminal alkynyl substituent. So let's show that. So we have our cyclohexane ring. It, in many ways, is unreactive in this whole process. So it's unchanged. And when you're drying your alkynes, again, sp hybridized carbons, so 180 degree arrangement of the bonds on either side of those alkenyl carbons. And so therefore, they're very linear as shown. And so now we've converted in these 2 steps, we've converted the acenyl group to an ethynyl group. Now we can use this alkylation strategy to increase the amount of carbon in our skeleton. And so let's continue by adding to this system. We will add some sodium amide to deprotonate the alkynyl group. And then we will add to this the appropriate alkyl halide. Now we only want to add a single carbon, so we only need a CH3 group, so methyl iodide could be used in this scenario. And so that will produce a 3-carbon, so I'm just going to show it like this, a 3-carbon alkynyl substituent. And now we're very close to our target molecule, but we will have to reduce this alkynyl group to the alkenyl group. Now note that what we produce here is a particular stereoisomer. It's the trans isomer, not the cis. And so if we want to control that stereochemistry, we have to choose specific reduction reagents. And as we saw in this section, if we wish to reduce that alkyne to a trans alkene, we use the dissolving metal reduction reaction, which is using sodium metal and liquid ammonia. And we saw that that is a radical reaction that will produce a trans alkene and not further react to the alkene. So this is the synthetic route that could work for this particular target molecule. Again, we start with bromination of the alkene to give us a dibromoalkane. We can then carry out successive E2 reactions and then a deprotonation if possible, most likely to give us the alkynide. We can quench that to form the neutral alkynyl cyclohexane, and then we can deprotonate that terminal alkynyl group, react it with the primary alkyl halide to increase the carbon skeleton, and then finally we can reduce that alkynyl group to the alkenyl group in a stereochemical specific way by choosing the appropriate reduction reagents. So in this particular example, I would refer to this as a 1, 2, 3, 4-step syntheses. It is possible to somewhat simplify this synthetic route. You'll note that in the 2nd and 3rd step, we generate the alkynide and then we quench it. there's nothing really stopping us from, instead of quenching with water, introducing methyl iodide sooner. And so it might just depend on whether or not you can carry out this complete synthesis in a single day. You may want to just isolate and purify this particular intermediate product first before carrying out successive alkylation reactions. But if you wanted to shorten this synthetic route to, in some sense, a three-step reaction, you could introduce methyl iodide earlier, and that would lead you directly to your new, larger alkynyl substituted cyclohexane. So yes, efficiency is important, but for our purposes, developing a synthetic route that is plausible is more important than the overall efficiency of your proposed route. So again, I'll just finish this video reminding you that this chart is quite helpful when carrying out synthetic route type questions. And as you can see in this section, we've now enhanced or expanded our reaction toolkit to include reactions and ways to form alkynes from alkenes. And we've then, through hydration reactions, introduced ways in which we can take our hydrocarbon backbone and incorporate the carbonyl. And so we've introduced two methods for carrying out hydration of alkynes that generates either a ketone or an aldehyde. So if you have any questions about synthesis and synthetic route type questions, by all means, send me an email and we can discuss it further. Thank you.